There we go. Okay, welcome back. So we started chapter 4, number theory or arithmetic, depending on how you want to see it. It's the same thing. So let's review briefly what we did before the break. Okay, hopefully you did take a look at some of the problems. I hope, maybe not, but anyway. Um, so here's a few I forgot how to write. A few reminders. Okay, so we are looking at the integers, right? So we've defined the notion of divisor. We've proved a few basic properties concerning divisors, multiples. The most important thing that we saw, the first thing that we saw, is the division algorithm, which tells you, and this is fundamental, that if you take any integer a, I might not be using the same letters that I used when I presented it, doesn't matter. If you take any m in z, which is bigger than 1, then there exists unique, and uniqueness is really important. There exists unique q and r integers such that you can write a as m times q plus r, where r is at least 0 and is strictly less than m. Okay, so basically what this does is you divide a by m, and you get a remainder, which is between 0 and m, strictly less than m, right? And we use this to define a couple of things, right? So we define a function, which is as follows: a mod m is the r in this theorem, right? It's unique, so this is well defined. Okay, so this is the function which returns this remainder. Okay. We also define a relation, which is related to this, but is, I lost a window here. I don't know where are you, window? There you are. Let's put this, sorry. There we go. Yeah. Okay, so the other thing that we defined is the relation, which says that two numbers are related or equivalent modulo m, right? So this is the notation. So I say that a is congruent to b mod m. This is a relationship between a and b. It's a binary relation on integers. So a is congruent to b mod m. This means the definition that we gave is that m divides the difference. Okay, and we proved a lemma that said this is the same as saying that the remainder when you divide a and b by m is the same. Okay, so another way of seeing this is as follows, right? So look at, so what is a minus b? That's the distance between a and b as integers, and you want that to be a multiple of m. Okay, so the distance between a and b is a multiple of m, right? So as you go from a to b or b to a, whichever, you're going to count a certain number of m's with no remainder, right? And another way of seeing that is if you look at the clock, the what I'd call the m clock, right? So arithmetic, that's where I want to go. Arithmetic mod m, so clock arithmetic, right? So I have my hours, if you wish, like this, right up to m minus 1. So this is 0 to m minus 1. So these are the possible remainders when you divide by m. Okay, so what does it mean now that the distance between a and b is a multiple of m? Is that, so this is the trick that we use, right? So you look at z as a line like that, right? So you've got 0, 1, 2, 3, and so on, and the negatives like this. You can wrap this line around the circle, right? So the 0 will go to 0. Let's use a different color. So 0 will go to 0. And then you can wrap the line around the circle, right? And what does that give you? It gives you the remainders of the numbers, right? So you're wrapping this line around the circle, and each number will fall on one of these remainders. That's the remainder by division by m. And what does it mean for a and b to be congruent mod m? It means that they're going to fall in the same place, which, if you think about it, makes sense, right? So if you go from a to b on the line, the distance between them is a certain number of circles, right? So you have to fall in the same place, okay? So that's a way you can see this maybe more geometrically, okay? And we define this arithmetic in Zm. Let me see where I am in my, okay, so let's go here. Sorry. Okay, so we define Zm to be this set, this circle, the set of values 0, 1 to m minus 1. And we define two operations on it, plus n. So a sum and a product as follows, right? So if you take any two a and b in Zm, you define a plus b, and the little plus to make sure that we understand it's a different plus, it's a different operation than the one from the integers, although it's similar. Okay, so this is what you add a and b the normal way, but you reduce this mod m. So you look at the remainder of the sum. Same thing for the product, a times b. You take a times b the normal way, and you reduce that mod m. Okay. Now, this is exactly what you think it is when you go around the circle. If you go, let's say, so for example, we had, let's say m is 7, right? So I've got 0, 1, 2, 3, 4, 5, 6, like that. Let's say I look at 5 plus 6. If I just follow the definition here, this will be 11 mod 7, and that turns out to be 4, right? But another way of seeing it is just going around the circle. So if you go here, if you go 5 units like this, and you add 6 units, 1, 2, 3, 4, 5, 6, you end up at 4, right? So that's the same thing. Okay, and if you multiply, it's exactly the same idea. If you had 5 times 6, it would be 5. You go 5 and you do it 6 times around the circle, or that's 30 mod 7, which is 2, right? So 5 times 6, that would be 30 mod 7. 4 times 7 is 28. It leaves a remainder of 2, like that. Okay, and so on. Okay, now I showed you a lemma which I didn't really explain, and I'm going to try to give you an idea of what it means. Okay, so we saw the following result. What am I doing? I have more stuff I can fit in. Let's go here. So we saw the following result, which said that the sum and product in the integers behaves well with respect to this clock. Okay, so basically so I'm going to just repeat the result, and I'm going to try to give you an intuition for it. Okay, so if a is congruent to b mod m and c is congruent to d mod m, then a plus c is congruent to b plus d mod m. Notice this is not the sum in Zm here. This is just the usual sum, okay? And it's the usual product. AC is congruent to BD mod m. Okay, so we saw this result here. So what does it mean? So we have two things. We have what's happening in Z here. We have the usual arithmetic of Z like that. And we have this new arithmetic in the small world here, plus m times m like this. And we have a way of going from one to the other, which is what you wrap this line around the circle, right? So the line here is wrapped around the circle like this, okay? What this lemma says is that when you transform things like this, the plus and product will be transformed the right way in the circle arithmetic, okay? So the lemma says, this lemma says that the translation of arithmetic operations from Z to Zm behaves well. Okay, so it doesn't get all screwed up when you multiply in Z. When you look at what happens in Zm, it behaves the right way in the sense that you can either multiply first, take the remainders, or take the remainders first and then multiply in Zm. Okay, so in other words, so A plus B, right? You can define. Let's do it in. Let's view it in a computational kind of way. That might be easier to understand. So to find A plus B mod m, we can either add in Z first, then reduce modulo m, or reduce first modulo m, then use, oops, not the product, the sum, like this. Okay, so this has a lot of advantages. In other words, what the mirror image in Zm respects what's going on in the infinite world. Okay, I'm going to try to illustrate what the advantage of this is, although you might not see, I'm not going to be illustrating this principle exactly directly, okay? But I want to give you the idea of why this should be interesting. So here's a little illustration, very, very elementary. Okay, and let me put that in quotes because you might not just try to see get the feeling of this. It's rather than the technical aspects, which I could write down, but it would take me like half a page, and it's just, you might get lost in just the technicalities, and that's not what I want to do. I just want you to see the philosophy, if you want, behind this. Okay, so consider the following equation. 2x plus 3 times 4yz minus 5 plus 6xy equals to 0. Okay. And suppose that I ask you, so question, find an integer solution. In other words, find x, y, z integers that will satisfy this equation. Okay, so find x, y, z, and z that satisfy. Okay, so you can mess around. I mean, you've rarely seen things like that, because now you have like 3 unknowns and a single equation. I mean, and it's not linear, right? You've been doing linear equations, and I'm guessing that you've reached the point. Have you seen Gaussian elimination yet in linear?
Yeah.
Yeah, okay. So theoretically, you know how to solve very big systems, a lot of variables and a lot of equations, but the equations have to be linear. This is not linear, right? So variables are multiplied together, so that's out the window. So in general, this would be much more complicated, especially if we're looking for integer solutions. That makes it even harder. But it turns out that if you stare at this equation for a few minutes and you have a few hints, you're going to see that it's actually pretty easy once you know the trick. The trick is the following. So there is a trick. So the answer, I'm going to give you, I'm not going to let you waste your time on this. So answer, there are none. And maybe some of you have seen it, but so here's the reason. So now I have to show. So again, let's go back to our previous topic of proofs and things like that. If I want to prove that there is a solution, all I have to do is just give one, and that's it. But to prove that there is no solution, I have to prove that no triple of integers that you plug in here will give you something that works, right? So that's infinitely many possibilities to check. So there must be a trick, right? So what's the trick here? Well, look at the integer 2x plus 3. If I plug in any x in here, I'm going to get an integer which is odd, right? For any x. Everybody agrees with that, right? It's 2x plus 2 plus 1. So it's even plus 1. So it's odd. What about 4yz minus 5? This is also always odd. Whatever you plug in for y and z, this is odd. If you're not sure about that, rewrite it, right? So this is 4yz minus 4 minus 1, or you can rewrite it as 2. This, I mean, if you don't see it, this is 2 times w plus 1, easy. Okay, you can rewrite it as 2w plus 1. Now, if you multiply 2 odd integers, what do you get? You get an odd integer. Okay, so 2x plus 3 times 4. Now you see where this is going. If you multiply 2 odd integers together, you're going to get an odd integer. Now, 6xy is clearly even, again, for any x, y, and z. So now I have an odd integer plus an even integer that's odd, right? So whatever integers I plug in, x, y, z, in this whole thing, if I plug those numbers in, 2x plus 3 times 4yz minus 5 plus 6xy is odd. Even plus odd is odd. But this is supposed to be equal to 0, so cannot be 0 since 0 is even. And that's it. Okay, so hopefully you saw what I did here, right? So I have an equation. I'm asked to find integers that satisfy the equation. In fact, there are none. And how do I prove that? I argue on what happens on even and odd. So basically what I'm doing, so what I did, and this is where I don't want to go, right? Because it's going to get a little technical. So, but essentially what we did is this. We reduced the equation. If you want to do it, you can do it as an exercise. Just see what happens to the equation if you just rewrite it in Z2, 0, 1, right? So we reduce the equation mod 2. That's what we did. Okay, and we know that whatever happens on Z has to be reproduced in a right way in Z2. So if there's a solution in Z, there has to be one in Z2. But if you look at what happens in Z2, and this is the argument we use basically, but I kept it at a higher level so that you'd see. But essentially, that's what we did. Okay. Now, maybe mod 2 would not be the right place to look. Maybe it would be mod 43 or mod 120, who knows? But this is a very, very common and very generic approach to certain problems, not necessarily just that kind of problem, but to many, many problems. Okay. So because the whole thing behaves well, you know that if something works on Z, it'll have to work on the ZM. If it doesn't work there, that it means that it couldn't work on the Z to start with, on Z. Okay, so that's a bit the idea behind this lemma and this whole thing. We are going to get back to this strategy in a deep way in next week, I think. Okay, all right. So that's what I wanted to do as far as review goes. So now I'm going to move. So that's section 4.1. Okay. Okay, so that's end of review of 4.1, and I strongly encourage you to go and look at the exercises. I should have a web work out soon, but it deals with some stuff that we haven't seen yet. So I'm gonna wait a little bit, but we're gonna get there. Okay, so 4.3. 4.3 is primes and GCDs. I think that's the title in the book. And this one has a lot of important stuff. There's Euclid's algorithm. And you remember we talked about the division algorithm, which wasn't an algorithm. Euclid's algorithm is an actual algorithm. And it's one of the greatest algorithms out there. It is just a fantastic algorithm. It's so smart and efficient. Okay, so let's start. I won't get to the GC. I just want to do the primes part right now. I have a lot of stuff to say on that. So let's start. So what's a prime number? You all know what a prime number is, but just to make sure, what is a prime number? You can define primes. You can have negative primes. We're just going to define them for positive, but it's the same thing. It's just a mirror image. So let n be an integer bigger than 1. Okay, then we say n is prime if its only positive divisors are 1 and itself. Okay, now if you don't add this condition that n is bigger than 1, that would make 1 prime. So 1 is only divisible by 1 and itself. But having 1 prime is very inconvenient. So we don't consider 1 to be prime, but it's a matter of convenience. We choose to define primes as starting the smallest prime is 2. Okay. If an integer is not prime, it's called composite, a positive. So yeah, n in Z bigger than 1. So if n bigger than 1 is not prime, we say it is composite. That's the name. Okay, so that means it has some positive divisor, which is neither 1 nor n. So that means it has at least 2 of them, right? So it can be written at, so let me put that as a remark. Yeah, it's a remark. I mean, you should convince yourself of this, but I think this is close to obvious. maybe not after 1 week of break, but if n is composite, or I should say, sorry, n is composite if and only if n is equal to a times b for some integers which are strictly between 1 and n. Okay, so the observation, of course, is that if you have a divisor which is strictly between 1 and n divided by that number will give you another divisor, but strictly between 1 and n. That's what I'm trying to say. So okay, so what are the first few primes? Here are the first few primes. I just forgot how to write the first few primes. 2. There's this old, I shouldn't say this joke, but 2 is an odd prime. Think about it. It's a bad joke. 2, 3, 5, because it's the only even prime, so it's odd in the other. Forget it. Here are the first primes. Did I miss anything? No. 23, 29, 31. 37 is prime. 41 is prime. 43 is prime, and so on. So these are the first few prime numbers. As you can see, obviously there's only one which is even, it's 2. And in fact, there are so many theorems out there where you always have to specify that the prime is not 2 because it's a weird prime. But it's prime. Okay, so these are the first few primes. And here is our first theorem. And I'm going to switch pages for it because it's too important. It gets its own page. Theorem. This is called the fundamental theorem of arithmetic. So don't ask if it's important. It's called the fundamental theorem of arithmetic. What is the fundamental theorem of arithmetic? It says the following. Let n be an integer at least 1. Then n can be written as a product of primes and this representation is unique. Unique up to permutation of the factors. So of course you can rewrite the order in which you write it, but otherwise it is unique. So the primes are like the atoms for the integers, right? So all the integers can be written as a product of primes, and this can be done in a unique way. Of course, you can reorder, but otherwise it is unique, okay? You might see now why it is inconvenient to have a prime number, because it would destroy this theorem. If you allow 1 to be prime, then you can multiply 1 by itself any number of times. So this is destroyed. It's not true anymore. So it is not convenient to have 1 as a prime. Okay. Now the proof, and you're going, oh no, not a proof. But I can't prove it right now because the main ingredient is induction, which we will see in chapter 4. Chapter 5. In chapter 5, we need induction. Okay, let me illustrate what this means. Some examples, some numbers. 100 So I want to break down 100 as a product of numbers, and I want to break down these numbers as much as possible. So eventually what I'm going to hit are prime numbers, right? So 100 is 2 times 50, 2 is a prime. 50 is 2 times 25, so that's 2 times 2 times 25, and then 25 is 5 times 5. So there you have it, right? So this is 2 squared times 5 squared. This is the unique way to write 100 as a product of primes. 2 is there twice, and 5 is there twice. 2 and 5 are primes, okay? 999. This is 3 cubed times 37. 37 is a prime. It divides 999. And so this is the unique way to represent 999 as a product of primes. So 3 is there 3 times and 37 is there once. Okay. 1024. If you're in computer science, you should know that one. If you're doing any sort of binary stuff or bytes and bits and whatever, this is 2 power 10. So this is the unique way to write 1024 as a product of primes, 2 power 10. What about 641? Of course, I knew these in advance, right? Although they're not very difficult because these are small numbers. I'll get to that in just a sec. 641, if you try to divide this by all sorts of stuff, you're never going to get anything interesting. This is 641. That is the unique way to represent 641 as a product of primes. It is prime itself, right? So when we talk about a product, of course, we allow a single number. If the number is prime, it's equal to itself, and that's its representation. That's it, okay? All right, so every integer can be, and you might have done this in high school. They might have asked you to factor numbers into primes as much as possible. And so you did that. If not, it's not really, there's nothing really new here. I mean, it's just basic arithmetic, right? I hope it makes, I think the theorem makes sense, right? If you intuitively, you start with a number, if it's the product of two numbers, and then you just repeat this, eventually you have to stop. But that's induction. I mean, we need to formalize this, but intuitively, if you keep dividing a number, eventually you have to stop. You're going to get numbers that you can't divide into products of smaller numbers. These are primes. So then you have it. The uniqueness is not so obvious. This is the hard part in a sense, right? So if you have two ways, maybe you could have two completely different ways of writing the same number with different primes. Maybe, who knows, but that's not possible, okay? This is not obvious, okay? I want to just take a little step to the side here to relate this to more computer science-y things. Here are some remarkable facts, which are like, some of these things are really fundamental. The first remarkable fact is this. So consider the following problem. So I'm going to, so your input, so basically I'm asking for a computer program, right? So my input is an integer bigger than 1. Right? The output is the prime factorization of n. Exactly what I showed you, right? Prime factorization of n, right? So if the input is 100, I want you to output 2 squared times 5 squared. Okay, so how hard is this? In the sense, do we have an algorithm which is efficient to do this? Answer, not yet. And probably we'll never have one, but okay. So it is believed It is believed I can't write. It is believed that there is no efficient. Let me put this like that. Efficient algorithm. No, let's not. No. Efficient algorithm to solve this problem. So in other words, if you write any program that does this, eventually when the numbers are really big, it's going to take a huge amount of time to do this. Now, what do we mean by efficient in this context? It means this. So by efficient, we mean this. I mean, there's a lot of technicalities that I'm just not even talking about, but to give you an idea. So efficient here means the running time is polynomial in log n. Now you're going to say, wait, why log n? Because that's the size of the input. If you write n in binary, how many bits does it take? Again, log base 2, right? So this is the number of bits to write n. That's what it takes, right? So that's the size of your input. So when this log n, so if you're polynomial log n, that's much harder than polynomial in n, right? So if you, I'm not sure this means anything to you, but it's you look at the number of bits and you want an algorithm that's going to output this factorization of the number n into primes. That is, let's say the number of bits, let's call it k. The steps will be, let's say, k power 10, for example, roughly, right? So it is, most experts believe that there is no algorithm that can solve this problem. If you can prove this, you will be, first of all, you get $1 million right there, and you'll get a really, really good job, and you'll be like super famous. Okay, so this is like, I mean, this is like huge. Okay, or if you actually find an algorithm that does this efficiently, you don't tell anybody, and you break all the public key cryptography codes that are in use right now, and then you make a lot of money illegally, but you will be caught. So this is your choice, okay? But there's probably not any such algorithm, okay? Now, the second remarkable fact, okay, I should add if you find one, you will make a lot of money. Okay, either way, yes, that's where I'm going. Now, about 94 is, that's the age of my daughters. That's 20 something years. 20 years ago, Peter Shor proved this. There is an efficient algorithm to factor. It's a quantum algorithm. This is by nice. This is a fantastic result by Peter Shor, 1994. So if you can build a universal quantum computer, which does not exist yet, which might not ever exist, that's another story. So there is an algorithm to factor efficiently on a quantum computer. So that's you're going somewhere else, right, with this. But on a standard computer, no. Yes, so you're right. I should have added, there is no efficient standard algorithm. I'd say. Okay. Now, there's a related result, which is pretty cool, which is the following. So here's another remarkable fact. So this is from 2002. And the people who did this are Agrawal, There's poor guy. I never, yeah, Kayal. I can never remember this guy's name, Kayal and Saxena. The first and last I can always remember. The guy in the middle somehow, I should think Kayak, Kayal. Okay. They prove the following. Here's the problem. Input n, an integer bigger than 1. Question, is n prime? Blech. Prime. So this is the problem primes. Okay. It looks a little bit like the problem I mentioned earlier, right? It seems a bit simpler, but it is in a sense simpler. Okay. And in 2002, these three people showed that there is an efficient algorithm to this. So they showed, so there exists an efficient algorithm. If we had like, I think maybe a week more or 2 weeks more, I could actually show you the algorithm, but it requires some fancy number theory, but not super fancy, which is surprising. That's why, I mean, this made a lot of noise because a lot of people were looking for an algorithm for this, and a lot of really smart people were looking for that. They couldn't find it. I'm not saying these guys were smart. They're smart. They found it, but it was surprising because the solution was sort of simple. It was sort of there. Nobody saw it. So that was pretty cool. So there is a polytime algorithm in log n to determine if a number is prime. If you're thinking, wait, can't we use that to solve problem 1? No, not in any obvious way. So yeah, okay. So these are higher level things that are of interest. I should put this here. No, not erase. Cut and paste. Let's put this here. Oh boy. Oh, that's this. That's what they proved. Okay. All right. So there is an efficient algorithm to determine if a number is prime. I don't think anybody uses it because there's a randomized algorithm which is like super fast, which everybody uses. But anyway, which is, this hunt for really big primes, which is very important for public key cryptography. Having big primes is important. So you have to be able to recognize when a number is prime or not. I mean, this is connected to all sorts of stuff, right? This is, so I give you a number with like 1,000 digits and you want to make sure it's prime. How do you check? And you have to, right? So it's, yeah. So this is, and we need big primes. We need, and you'll see why in next week, 2 weeks. Okay, all right. Again, if there are any questions, please do not hesitate. So let's go to our next theorem. Oops, sorry. There we go. So here's our second theorem, which is easy, which is useful. It's cute. So if an integer is composite, then, oh, man, then it has a prime divisor P such that P is bigger than 1. Obviously, it's a prime, but is less or equal to root n. Okay, so first thing you might ask is, so what? Who cares? Who gives a cut? But this is useful for small numbers. This gives you a nice little method to find the prime decomposition. I'll show you, and to check if a number is prime. Unfortunately, it's not sufficient to get something which is fast all the time. For big numbers, it's not fast enough. But here's the proof. Here's the proof. Okay, and it's an important proof because it actually explains why this is true. Maybe you can sort of see why this is true, but let's just write it out. Okay, so n is composite means that we can find a and b such that n equals a times b, and a and b are strictly between 1 and n, right? That's what my comment, the comment I made earlier. Okay, so it's not a prime, so you can factor it in as a product of two numbers. Now I'm interested in the smaller of these two numbers. It might be b, but I'll just call it a if it were, I just renamed them, right? So without loss of generality, without loss of generality, a is less or equal to b. Okay. Now a has a prime divisor. By the fundamental theorem, every number can be written as a product of primes. It might be prime itself, but it certainly has a prime divisor. So by the fundamental theorem of arithmetic, a has a prime divisor p. And this is the prime I want, okay? Or any such prime will work. So now, hopefully you see this. Then obviously, if p divides a and a divides n, then p divides n, right? So p divides n, since p divides a divides n, right? This is one of our little basic little lemmas we saw a century ago. And p must be less than root n. Why? And p, okay, so p is certainly less or equal to a. Yeah, that's, yeah. And I claim that a must be at most root n. Now we did this argument at some point, but look, a times b is n, right? So a bigger than root n is impossible because otherwise, so this is a little proof by contradiction, right? So if a is bigger than root n, then b is bigger or equal to a bigger than root n. So it means b and a are strictly bigger than root n. So it means that a times b is strictly bigger than root n, which is n. That's a contradiction. Is that okay? If you multiply two numbers to give you n, at least one of them must be less or equal to root n. I think we stated it precisely that way a long time ago. So it means that if I factor n as the product of two numbers, one of them is less or equal to root n, and it has a prime divisor, so that's the prime I want. Okay. Is that okay for you? Does that make sense?
What is by FTA?
Oh, fundamental theorem of arithmetic. Yes? No?
Yeah, thank you.
Okay. Okay. So any composite number has a prime divisor at most root n, and obviously bigger than 1. Okay. How can I use this? Okay, so here's okay, let's put a little square here so you know that's the end of the proof. Here's an example. Show 101 is prime. Okay, so I want to show that 101 is prime. The last theorem says if it's not prime, it has a prime divisor less or equal to root 101, right? So last theorem says if 101 is not prime, there exists a prime p that divides 101, p less or equal to root 101. Okay, so if you're not prime, you have a prime divisor at most, root of your number. What is root 101? Root 100 is 10. Root 101 is certainly less than 11, right? So root 101 is less than 11. That's clear. Okay. And so if 101 has a prime divisor less than 11, it has to be either 2, 3, 5, or 7, right? So P must be 2, 3, 5, or 7. And we're going to rule them out one after another, and that's easy, right? So can P be equal to 2? No. Does 2 divide 101? No, 101 is odd. Can P be equal to 5? No, 5 doesn't divide 101, right? It doesn't end. It's not a multiple of 5. You know the trick. And I will review a few tricks. Oh, I forgot 3. That's smart. No. 1 plus 0 plus 1 is equal to 2. If that means something to you, great. If it doesn't mean anything to you, you're going like, what the hell is he talking about? I will get to there in just a sec. See below. What about 7? Well, I'll just divide 101 by 7 and see what happens. 1 times 7, 31, 4, 28, 3. So 101 is 7 times 14 plus 3. So no. Right, this is the unique representation of 101. When I divide by 7, remainder of 3, it's not 0, so no. So 2, 3, 5, 7 do not divide 101, so it's a prime. Okay. Now the silence is unbearable. Is this okay?
Yeah, that works.
Yes. Yes. Okay. Let's. Why? This is weird. Okay. Okay. Let's just do this. Okay. Some tricks. Basic tricks for divisibility. This is cool. Divisibility. Rien m'amuse. Okay, so 2 divides n. If I give you like a huge number, how do you check if 2 is a divisor?
If it's even.
And how can you check that really quick?
If it ends in 0, 2, 4, 6, or 8.
Exact. Yeah, check last digit. Exactly. This is the only way. Okay. 5 is even easier. Right? Multiples of 5 always end in 0 or 5. And if and only if, check last digit 0, 5. Super efficient algorithm. And you see how efficient this algorithm is because the size of the input is actually doesn't make any difference. I give you a number which has a zillion digits. You just check the last digit. So you just have to get to the last digit. That's it. That's the hardest part. So, so these are easy. What's the next easiest? Well, 4 is easy, right? But let's forget about that. Let's look primes. Let's just look at primes. 3. Maybe you've seen this trick. Maybe you haven't. This is a very cool trick. If you've never seen this, then it's like some friend of mine said, oh, I never saw such and such film. I said, oh, you're so lucky. You get to see it. It's a great movie, right? I've seen it like 20 times, so I can't. Okay. Anyway, Ignorance is bliss. 3 divides n. Some of you know this trick for sure. So you look at the digits and you add them up and you get a smaller number than what you had. And so you repeat, you repeat, you repeat. And eventually you're going to get a number which is either 0, 1, or 2. And that's it, right? I mean, mod 3. So add the digits. If divisible by 3, yes. If not, no. Right? So for example, 101. 101, the sum of the digits is 2, not divisible by 3, so the answer is no. Let's do a bigger one. Let's say 10102971101. I want to check, is this divisible by 3? I haven't proved this, right? I'm not giving you a proof. It may be an exercise. It's probably an exercise. It's not super hard, but ooh, I've lost people. Okay, so I'm gonna go 1 plus 1 plus 2. The 9 I don't need to add, right? Plus 1 plus 1 plus 1, but I'll put it there. And then this is 23, is it?
Yeah.
Yeah. And so then I repeat, I can repeat. Not divisible by 3. So the answer is no. So this is very efficient too, right? Not as efficient as for 2 and 5, but it's very efficient. The same trick works for 9. It is exactly the same trick. By the way, it's not prime, but I'm just giving you. Okay. 7, unfortunately, there's no real nice trick for 7, but 11, there's a really cool trick. It's just a little trickier to explain, but here's the trick for 11. I'm just going to give you an example because it's hard to write down, but you'll see how this works. Let's say do I have a cool example? I don't know. No, I don't. But let's just try. 302119710222115. I'd like to know if this is divisible by 11 or not. So here's what I do. Again, this is not too difficult to actually. I think this one is easier to prove than the other ones. But what you do is you look at the digits. The first, third, fifth. You just jump a digit every time like that, and you add those up. So that's 3 plus 2 plus 1 plus 7 plus 0 plus 2 plus 1, which will give you 16. Okay. Then, you take the other digits and you do the same. So then you get 0 plus 1 plus 9 plus 1 plus 2 plus 1 plus 5. I just did this at random, so I have no idea how this is going to work out. That's 19. Now, what's the test? The test is the number will be divisible by 11 if and only if these two numbers are congruent mod 11. Okay, so 16 is not congruent. Oh, I wrote it backwards. Brain cramp. 16 is not congruent to 19 mod 11. Sorry. So, no. And it's if and only if. Okay, so that's the trick. So if you take a really big number or a smaller number or whatever, if you add the digits jumping one each time, and you do that for both sets of digits, then the number is divisible by 11 precisely when these numbers are congruent mod 11. Okay, so here's an example. 1001 is divisible. You can see it immediately, since 1 plus 0 is congruent to 0 plus 1 mod 11, right? It's immediate. So it's very quick. It's immediate, so it's very quick, yeah. Yes. What time is it? 15:05. Let me just do a couple more examples. Man, I didn't get to where I wanted to get, but okay. Okay, so if you're doing math contests, these are like usually very useful. Let's go here. Okay, so here is another example. Find the prime factorization of 7007. Oh, well. Okay, so as I said, there is no efficient algorithm to find the prime factorization, but of course for small numbers you can do it. I mean, it's not if I give you a number with 100 digits, then it becomes extremely painful. But even with a machine, okay, so but here you see, okay, so clearly, I mean, this you can divide by small primes, or you can check with these tricks, right? So is this divisible by 3? No, right? So note, it's not divisible by 2 nor by 3, right? So note 2 does not divide. That's clear. You look at the last digit. 3 doesn't, sorry. 3 doesn't divide 7007, since 7 plus 7 is 14. 1 plus 4 is 5. You don't have, I mean, we know 14 is not divisible by 3. 5 doesn't divide. 7 does, right? Okay, so 7 times 1001. I can do that, right? 1001, yeah, my tablet is going to die soon. 1001 is, we said, is divisible by 11, right? So we saw this is divisible by 11. Let's do it. 11, 9. What am I? Sorry. What the hell am I doing? 1, 1, 1, 91. So this is 7 times 11 times 91. And 91, you have to check separately, right? It's divisible by 7, right? So 91, you have to check. Again, 7, there's no cool trick. 1 times 7, 2, 1, 3. It's 7 times 13. So this is 7 times 11 times 7 times 13. So it's prime factorization. If you write it in increasing factors, is this. Bingo. Okay. So
you basically have to check with the tricks we saw earlier and then just test everything else.
yeah, I mean, the tricks just make it go a little faster. That's the idea.
Okay, perfect.
Yeah. The one for 11 is kind of cool because it's really fast, and 11 is sort of annoying. It's like bigger. 2, 3, 5, easy, right? 7 is the annoying one. You have to divide. There's no other way. Yeah. What time is it? Okay, so yes. So next time I will prove a very old theorem. which is due to Euclid. I'm going to state it here and then I'll prove it next time. It's really cool. So next time, that's tomorrow, I'm going to prove this so this was proved like 23 centuries ago. And it's like super important for today's cryptography and for the web. It's pretty cool. So this goes back to Euclid. There exist infinitely many primes. Exist infinitely many primes. So I'm going to prove that next time. It's a very, very nice proof. And that's why it's so annoying when every once in a while in the papers, you see an article that says, oh, scientists have found the biggest prime, which is like, but there is no such thing. They found the biggest prime such that, maybe, but not the biggest prime, but you always see that. It's like the Nobel Prize in economics. They always, every year they talk about that, and there's no such thing. But anyway. Okay. So any questions, comments? I'm not going to ask you to tell jokes because that doesn't always turn out well. Okay. All right. So I will see you next time.